Looking at circular orbits, so I've scrolled through to section 6 on my data booklet to see if there's anything useful here. Okay, planets in a circular orbit, we're given the mass of the different planets and stars and their distances. Okay, explain why a centripetal force is required. This is one of these questions which, if you look at the mark scheme again, you'll see various bits, and you're kind of just being asked to pick and choose the best way of you explaining it. Okay, the way I would go about it is this. If we want to have circular motion, we require it to have a changing velocity. Now, a changing velocity implies acceleration. And so therefore, in order to achieve this, we need a force. Any acceleration must be caused or brought about by a force. The force in circular motion must be centripetal. In other words, it must be directed towards the center of the orbit. If it was not directed towards the center of the orbit, we would not achieve circular motion, and therefore, otherwise, the circular orbit could not be obtained. All right. So in terms of getting marks here, in terms of explaining here, this is a fairly thorough, in-depth explanation. I'm fairly confident that would get you 2 marks. In terms of where the marks would come, certainly the idea that a force is required because we have a changing velocity, and that force must be directed towards the center of the orbit. You remember these diagrams we've had of the tangential speed and the angle between the force and the velocity always being 90 degrees. And that is really a key point here to include in our answers. Okay, we're then asked to calculate the value of the centripetal force. This is why we've got the book open. We look for F equal to G mm over r squared. Why is that the case? Well, it's because in this case, the gravity is providing the centripetal force. Okay, so really, when it asks you to calculate the centripetal force, it's actually asking you to calculate the gravitational force. We've got our values up here, m, and r, and it's a case of subbing into our equation 6.67 times 10 to the minus 11, which I'm sure you've got imprinted on your brains by now, and coming up with a number, massive number here, 8.8 times 10 to the power of 23 newtons. Don't be surprised that this is a big number. It's completely understandable. We are dealing with a planet orbiting a star here. Slightly harder is to look at the spacecraft being launched from the surface to escape the star system. Now, in order to escape the star system, it has to overcome the gravitational field due to both the planet on the left and the star on the right. We're on the surface of the planet, and we want to escape the star system. So this could be simply our solar system. Okay. We want to calculate the gravitational potential due to this planet and the star at the surface of the planet. Well, in order to do that, we add together the 2 potentials due to each of these. Okay, again, looking at this time, scrolling through to our fields, we know that the potential is Gm over r. Well, in this case, we've got Gmp of the planet, Rp of the planet, and Ss of the star as well. Now, it follows that all you have to do is put in the values. Okay, we're on the surface of the planet, and so therefore my r planet is simply the radius of the planet. Okay, we're at a distance of 4.4 times 10 to the 10 meters from the star. Okay, I think we can ignore the radius of the planet in this case. Okay, so that's where our 2 values here come from. We've got our 2 masses, and we've got g again, and then we're ending up with a value of minus 4.9 times 10 to the 9. In other words, approximately minus 5. Again, in these kind of questions, it's a showing question, and quite rare for a showing question, it's a 3 marker. They've given you the answer, but there's tricky bits. Why is it 3 marks? There's things that we have to pay attention to, like the units. Converting this into meters is certainly one, but also key on the mark scheme is to look at the fact that you must include all of the substitutions in your answer. So it's not enough to simply write this down and then get the answer. You must show your values. So if you've lost a mark here, that may be because you haven't shown the values. In my world, you would always put the values in where possible. Okay, estimating this escape speed. Well, there's an equation for the escape speed, okay, which is twice Gm over r. Okay, and there's another way that you can think of it as well. Okay, escape speed, we've got kinetic energy at the beginning equal to the change in the potential energy. kinetic energy, half mv squared. Potential energy is simply the mass multiplied by the potential at that point. And the potential at that point is this value that we've calculated in 6c. You notice here we can calculate the m, cancel the m's. Okay, we're not told that. And we can rearrange, remembering that there's a minus sign here. That's going to be crucial later because our potential itself has a minus sign. Okay, and so therefore we've got v is equal to the square root of minus 2 times v, minus 2 times, forgot my minus sign there, minus 5 times 10 to the 9 gives me a value of 9.91 times 10 to the 4. And what this says is in order to overcome the gravitational pull of this star system, then we are going to have a speed of approximately 1 to the 5 or 10 to the 4, 10 times 10 to the 4, meters per second. Okay, that's all for question 6.